Okay, let's dive right into this. Welcome back to another explainer, where we take these massive, complex subjects and just break them down into their clearest components. Today, we are looking at the absolute bedrock of the mathematical universe. We're talking about the architecture of numbers, specifically calculations and the order of operations. If you've ever looked at a string of numbers and wondered, how on earth did one person get a completely different answer from someone else? Well, it literally all comes down to the rules we're going to explore today. This isn't just about blindly punching digits into a calculator. It's really about understanding the logic, the flow, and the strict hierarchy of math. So, here's our roadmap for today. First, we'll start with powers and cube roots. Then, we'll visualize things with graphs. Move on to understanding reciprocals. And finally, bring the whole shebang together with the order of operations. Let's get to it.
All right, Section 1, Powers and Cube Roots, the basic building blocks of numbers. Let's look at the why before the how. Imagine an actual physical cube, just sitting there in three-dimensional space. If that cube has sides that are exactly 2 units long, 2 units wide, and 2 units high, it perfectly occupies exactly 8 cubic units of space. Why? Because 2 times 2 times 2 equals 8. So, when we ask for the cube root of 8, we're basically just asking, hey, what is the length of one side of that perfect cube? And the answer, of course, is 2. The cube root essentially just deconstructs that volume right back down to its foundational measurement.
Now, theory is fantastic, but application is what actually gets the job done. If you're working through a complex problem, you've got to know how to execute this on your hardware. This specific cube root function button, which you'll find on almost any scientific calculator, looks like your standard square root symbol, but it's got a tiny little 3 tucked right into the notch. Finding this exact button bridges the gap between that theoretical math we just talked about and practical, flawless execution when you're actually crunching the numbers.
And watch how this builds into something kind of surprising. The cube root of 64 is 4. Simply because 4 times 4 times 4 is 64. Pretty straightforward, right? But look at that second point. The cube root of negative 64 is exactly negative 4. Why is that? Well, a negative times a negative is a positive, but when you multiply by a negative a third time, it flips right back to negative. So negative 4 times negative 4 is positive 16, and 16 times negative 4 gives you that negative 64. But here is where you really need to pay attention. Look at the final bullet point. When we root a number by an even power, like taking the fourth root of 625, we actually get 2 answers. Both positive 5 and negative 5 work. It's crazy, but negative 5 multiplied by itself 4 times perfectly cancels out all the negatives to give you a positive 625. It's just a brilliant little quirk of mathematical architecture. Moving right along to Section 2, Visualizing with Graphs, the shape of mathematics. Now, what's really interesting about this slide is how it brilliantly illustrates exactly what I mean. Here we have a simple data table for the equation y equals x squared. Let's just trace the flow of this data. As x increases by just one single unit at a time, 0, 1, 2, 3, 4, 5, look at what happens to y. It goes from 0 to 1 to 4 to 9 to 16 to 25. It's a literal explosive progression of growth. If you were to actually plot this out on a graph, it wouldn't be some straight, boring line. No way. It would curve upwards sharply into this beautiful parabola. By organizing the math into this table, we can instantly see that squaring numbers causes them to just accelerate away from 0 at an increasingly rapid pace.
Section 3, Understanding Reciprocals. Flippin' the script.
This definition is incredibly straightforward, but I really want you to lock this into your memory. The reciprocal of any number is simply 1 divided by that exact number. That's it. It's just a simple inversion. But don't let the simplicity fool you. It's a super powerful concept to have in your toolkit. Let's look at this comparison to see how it actually plays out in different scenarios. On the left side, we have a nice normal whole number, 10. Following our rule, 1 divided by 10 gives us 1/10. Easy enough. But what's really interesting is what happens on the right side when we start with a fraction. The reciprocal of 2/5 is 5/2. When you're dealing with fractions, finding the reciprocal simply means flipping the fraction entirely upside down. The top number becomes the bottom number, and the bottom number becomes the top. Simple as that. And just like before, let's ground this theory in the real world of your calculator. This is the reciprocal button. It usually looks like x to the power of -1. Hitting this button gives you an instant fraction flip. When you're thick in the weeds of multi-step algebraic equations, knowing exactly where this essential shortcut is will save you so much time and prevent those annoying, careless manual errors. All right, we have arrived at the climax of our explainer. Section 4, the order of operations, the absolute laws of the math universe.
Okay, this is your classic wait what moment in math. We have nearly identical numbers on both sides. Equation A is 2 plus 3 times 4. Equation B is 2 plus 3 times 4, but with brackets around the 2 plus 3. Notice the drastic difference in the results. Equation A equals 14, equation B equals 20. How on earth can the exact same numbers and operations yield completely different outcomes? Well, it's because math relies heavily on convention. It relies on a super strict predetermined priority list so that everyone, everywhere in the universe, gets the exact same answer.
So the crucial point here is memorizing this specific 4-step hierarchy. This is the actionable checklist you literally must run through every single time you see an equation. Step 1, brackets always go first. Step 2, evaluate any powers or roots. Step 3, tackle your multiplication and division. And finally, step 4, resolve the addition and subtraction. If you apply this exact order to equation A from the last slide, you do the multiplication first, right? 3 times 4 is 12, plus 2 is 14. In equation B, the brackets demand priorities, so 2 plus 3 becomes 5, times 4 equals 20. The rules completely dictate the reality. Let's walk through these final examples together, just carefully tracking the logic. Look at the top equation, -4 multiplied by, in brackets, 8 plus -3. Following our brand new rules, the brackets are evaluated absolutely first. 8 plus a -3 gives us a clean 5. Then we multiply that 5 by -4, giving us -20. Now look at the bottom equation. The numbers are identical, but the brackets are gone. It's just -4 multiplied by 8 plus -3. Without those brackets, multiplication jumps right to the front of the line. -4 times 8 is evaluated first, giving us -32. Then we add the -3, pulling us even further down into the negatives.
Which brings us exactly to -35. There is a deep, deep satisfaction in looking at a messy jumble of numbers and operations, applying a strict set of rules step by step, and arriving at one unquestionable, mathematically pure final answer. It completely takes the guesswork out and replaces it with absolute logic.
Which leaves us with a really fascinating thought to wrap up this explainer. We've established that the order of operations, brackets, powers, multiplication, addition, dictates our entire current understanding of mathematics. It is literally the convention holding the math universe together. But as we push into the future, dealing with incredibly complex quantum computing where multiple states exist simultaneously, will these strict, linear, traditional rules hold up? Or are we going to have to invent an entirely new architecture of numbers? It's definitely something to chew on as you continue to build your own mathematical foundations. Thanks so much for joining me on this explainer, and I'll see you in the next one. Keep learning and keep looking at the structure behind the numbers.